I welcome all of you to this third session. So far, we have discussed water budgeting, and then I have also introduced you the water budgeting tool, various aspects of it, how to calculate, how to input the data, and then how to see the result of the water budgeting tool. And today, we are going to discuss about water auditing and how it is different from the water budgeting. Let me go to the my presentation and then start this. So this water auditing is something a relatively new subject, and also it is something an evolving, and then uh, it is not something that like water budgeting, everything is already defined. The recharge components and the extraction components are already defined, and then you do it in a very systematically in a already well defined methodology. But water auditing is a collection of methods you apply depending on the situation that on hand. So today I am going to explain water auditing and various concepts of it from by using various case studies. Some case studies I have taken from agriculture, some from the urban areas, and some from industries. And then you will be able to understand how this auditing is approached in different contexts, and then what are the complexities involved in it. First, let us begin with the definitions. Here you see that there are three definitions are given, and there are all the three definitions are relevant in their own context. Let me explain you start from the definition one. It says that it is a method of identifying leakages and plugging wastage of water in its use process. See, water auditing is a method of identifying leakages and plugging the wastage of water in its use process. Here is the first time that we are talking about the use of water for a particular purpose. In the water budgeting, we never talked about water use for a purpose. We never talked about leakages, plugging of wastages. We did not talk about how water is used. Only we were looking at different components of extraction, different components of recharge, and then we were trying to quantify those components and balance them, put them into an equation, and then balance that. If you remember, we have talked about precipitation is equal to various recharge components and then extraction components. So that is how we have built water budgeting equations. But here we are first time talking about water use and how that use is taking place, whether the use is taking place efficiently or are there leakages. So this is the first definition, and then let us go to the second definition. It says that the process of quantifying and improving the water productivity. It again, I am using a new word here, water productivity. What is this water productivity? So we heard about the productivity in the context of agriculture. We say that there is a crop, and then crop has yielded about 10 tons per hectare. That is called the productivity of that particular piece of land and that crop. But in the context of water productivity, it is the amount of food grains, for example, in agriculture, amount of food grains produced by using 1 unit of water is water productivity. If it is in the context of, let us say, a, a, a car manufacturing unit, say an industry, then the amount of water that is used to make a car, whether we are using more water, less water to produce a car, that is called the productivity of water. So here the second definition says that it is the process of quantifying and improving. So one is that quantifying how much water is being used for a given process, and then second part is that improving that. See, is there any way of reducing the wastage of water, increasing the efficiency of using water? That is how it looks at. So water auditing is that process. Then finally, there is a third definition which says that it is study and optimization of water footprints. It is again a new term has appeared here. Study and optimization of water footprints of a system having multiple water use components. Let me explain the system first. A system means it has a collection of different components, collection of different units where water is used for different purposes. Altogether is called a system. And then there is a term called water footprints. See, it is similar to water productivity. So, water footprint may be defined that how much of water is required to produce a good water. How much of water is required to produce a certain amount of food grain. 1 kg of say rice requires so much of water. So that means the water footprint of this rice is so much. See, like that, it is the amount of water that is required to produce a particular service or a good. Let us take the same example of the car and then apply here. Suppose in the car making unit in an industry, there will be several components, several units in the industry. One unit probably may be manufacturing the wheels, and then one unit may be manufacturing the body of it. Another unit may be wheels and other parts, and the steering wheels and or the internal chairs, and then various other components. Maybe another unit is dealing with the engine, another unit maybe is dealing with the electronic components. So all these processes of manufacture in different units require some amount of water, and then when you see that there is a multiple components like that, and then the multiple water used components all together is called a system. So an industry is a car making industry is the system which has several use water use components. So in that case, the water footprint, let us say, of a car, the- if, to produce a car in its final shape requires certain amount of water. Then if you do a study on that and then try to optimize the water footprints of that system, then it is also called water auditing. So these are different definitions which are from different perspectives. One may be in the context of industry, one could be in the context of in a urban and agriculture perspective. But all these definitions point us towards the difference between the water budgeting and water auditing. Let us take the case of see, we all work in some organizations, and then these organizations they develop a plan for the next year, say 2021, 21, 22, for the current year. So we have these are the sources of funds that we receive. I have income from rents, I have income from grants, I have income from consultancy work or some other income. My fixed deposits earn some interest, and these are all my incomes. And then I plan to spend these money, my income, to maybe to salaries of the staff, to the travel, and then to do some activities on the ground, to conduct some workshops and meetings. Like that, every organization makes a plan and also a budget, how to spend their resources. So, but in that process, that is a an internal process where you allocate some money for different activities, and then we can say that that is water budgeting like a process. It is the funds are budgeted like that. But here we don't ask any question about whether uh, this much money is required for this purpose, whether this money after spending, whether it's spent unnecessarily for a particular activity. But those questions are asked by a, tell me who asked those questions. See, they are the auditors. So either maybe internal or statutory auditors, they end of the year, after the money is spent, after your activities are done, when auditors come and then look at these expenditures, they may ask you the questions. Here you have spent some money, but there is no activity allocated. There is no this is that activity is not part of the plan. Maybe there you have spent a lakh more than what should be. It is expenditure. You have wasted the money for a particular activity. They may also say that, see, here there is a sorry, there are certain activities where you have underspent. You have not spent whatever is allocated for those activities. So this is a kind of an audit that takes place. So similarly, in water auditing, so we examine how water is used for various purposes, whether water is efficiently used or overused or wasted, whether there is any inefficiency in the way we use the water, and then try to address that, improve it, quantify that, and then see if there is a possibility of optimizing that our water use, optimizing our water use. That is the ultimate goal of any water auditing exercise. So also, we sometimes refer this to water footprint study also, in generally in industrial parlance. But whatever the terminology that we use, there are people using saying that water balance study, water supply balance study, water budgeting, water footprint studies. All that is like it is nothing but adding more confusion. But I would say that there are only two things. One is the water budgeting, another is water auditing. We have already defined what is what through these definitions. Now let us further go to discussion on a case study. This is a very, very simple case study related to agriculture. And then I have taken, for making it much more simpler, one individual farm. There is a farmer, just a second. There is a farmer, and then farmer has a borewell here, or tube well, whatever you call. So he pumps out some water, and then he applies it for irrigating his piece of land. He has about 10 acres of land, let us say. And then he cultivates three crops: crop 1, crop 2, and crop 3. Between these three crops it is divided, so the maybe 4 acres, 2 acres, 3 acres, like that. He has been cultivating that, and water is used to irrigate these three crops in a given season. Now, if you look at the draft from the borewell, we have already discussed while discussing about the water budgeting tool. What is a unit draft and what is the draft from a borewell? See, unit draft. Here is the unit draft. Unit draft is the amount of water that pumped out from a borewell for a, say, per 1 hour. For example, if a given borewell has an yield of 8,000 liters per hour, that is the unit draft per hour. So what we are interested in is, we are interested in the draft from the borewell. So that means the amount of water that is taken out, extracted. So this simply, if you know the yield from the borewell in terms of liters per meter cube per hour, or liters per hour, then multiply it by number of hours it is pumped for throughout the day, and then multiply it by number of days of operation, then you get unit draft of that borewell. See, because it is just one borewell, I am saying draft of the borewell. If there are 100 borewells in a given area, then we said that it is the unit draft, average unit draft, and then multiplied by the number of wells. But in this case, we are discussing about only one well. So that is the draft here from this borewell. So we can easily calculate that to the nearest possible accuracy. And then on the right hand side, because we already know that these crops have certain water amount of water requirement, and then based on that, if you apply this crop water requirement method, and then calculate the water requirement or water consumption by these crops, that's what exactly we did in water budgeting tool. We calculated the draft from the borewell, unit draft, using unit draft method. We also calculated the extraction using the cropping pattern method. But we there we did not compare these two. We only saw them as the alternatives. We were using a crop water requirement method for basic calculations of extraction for irrigation purposes, and then we also introduced the draft method, unit draft method, as an alternative, as an optional method. But here I am now trying to compare these two. That's where these auditing principles come in. So the total water requirement of these three crops is calculated in terms of crop water requirement method. Now, if I try to compare these two, So yeah, I have same amount of water, same thing. I have calculated in two different ways. One is the draft, and another one is the water requirement. So just guess if whether draft from the borewell will be more than this water requirement of the crops. Do you think that it is less than the water requirement of the crops, or these two are the same and they will be equal? It is quite possible that any of the three are true. See, because, see, for example, when you take the first case, more than draft is more than the water requirement. That means you are drawing more water from the borewell, applying some of it that water to the crops, but there is some excess water is also drawn from the borewell. Probably that goes out as an excess flow out or the wastage that is going out. That's quite possible. And in the second case, let us see if it is less than this. So what happens if it is less than this? So you are drawing less amount of water than what is required by the crops. So that means you are not giving enough amount of water to the crops. So the crops may not perform and then give you the optimum yield because of the water shortages it is experiencing in that case. Then the third case is this one. So this is the equal case. That means you are precisely drawing amount of water that is required for irrigation. So probably that is there is no excess flow. There is no excess flow at all, and then just sufficient water is drawn. So all these three cases are possible. But here these are the questions that we ask in this. So whether water is used efficiently. In the case of number one, so definitely not. You are not using water more efficiently. You are drawing more water and you are wasting some of the water. It is going out. So there is a possibility of optimizing how much water is required. So let us draw only that much amount of water so that you not only save water but also the cost of pumping, the electricity consumption involved in the pumping if it is a borewell. So just now we discussed a very simple case of one borewell and water being pumped out for cultivation, irrigation for a small piece of land and by an individual farmer. But now we have come to let us take a look at a complex application, more complex one. Here there is a source of water, but this is a lift irrigation scheme in this case, and then water is being lifted out for the purpose of irrigation from either a single or a multiple source of water. It need not be a well also. It could be an irrigation canal or an irrigation tank. But let us, within this very simple case, let us say that there is a single water source and then water is being pumped out from that and then it is put into this canal, which is a main canal. It is an open canal and it carries water to the agriculture lands. And then the length of this canal is approximately 2 to 3 kilometers long. So it is a long distance pumping, and then a network of pipe and then canal combinations are there here. See, if you look at this network, the main canal is an open canal, and then there are some branches taking off from different points, and these could be here. There is one branch canal, there is another one branch canal here, so there are four or five, and then they are open channels and open canals, but there are certain points where these pipes are taking off from this. Farmers might have installed some pipes and some farmers are using open channels, and then water is taken to the agriculture lands where the irrigation is applied, and different colors of the lands represent different kinds of crops, crop 1, crop 2, crop 3, like that. The farmers as per the farmer's choice. So this is a lift irrigation scheme. Let us assume that there is approximately 200 acres of land belonging to something around 150 farmers or 120 farmers. Here, it is because it is water is being pumped out from this water source. There is some element of energy use also. That means, let us say it is electricity is used for pumping, and in that case, it is not just the water that is also important, but also the energy is important. Electricity use is also important. So whenever you pump water, electricity is consumed, and then most of the cases in many places, farmers together meet the cost of the electricity. There are exceptions, but in some states it is also free, and then the burden is not on farmers. But still, electricity is consumed, and somebody else is paying for that. So that is why we have to think not only in terms of optimizing the water here, but also optimizing the use of electricity for pumping. Here, uh, let me explain you. So, what is the situation? So, after water is being pumped out and put into the main canal, some water goes into the these branch canals, and then it reaches the agriculture lands, and also it reaches the agriculture lands to the tail end. But the tail end, there are certain problems. The people, farmers complain that the water is not reaching. The water is sufficient. Water is not reaching them. See, that is one problem. The second kind is that, okay, there is a while the water is passing through this main canal, there is some seepage losses from the bed and sides of the canals, and that loss is also a significant one. That is the reason that some of the water that is pumped out is lost. So here it is written as seepage losses from the open canals. There is also some amount of water that is going out as excess outflow. So it all depends on how the scheduling is planned. So if water is applied to the crops when there is no requirement of water, for example, there is a rain today, and then if you try to give water lift and then give to water to the farmers, then probably very few will use the water, and most of it will go as the excess outflow. That means it is a waste for us. So this is the problem. So these two are loss components for us. And then there is also a possibility of these canals having certain amount of evaporation losses when the water is stored or it is flowing in them. There could be also some leakages from the pipe joints, and this is also one loss that we can quantify and then take into the account. So if you compare this equation, on the left hand side there is a draft from the water source. On the right hand side, we have crop water use, and then there is a draft and there is a crop water use, but there are several loss components which are added to this. So in the previous case, because it was the length of the distance between the water source and the land was very short, it is almost there nearby. So we did not consider any of these losses except these excess outflow. But here, in this case, there are several other elements are coming in. So, in case we want to address the problems of tail end farmers, the water shortages or excess water outflows because of it could be wrong irrigation scheduling, or it could be due to continuous pumping and excess water, putting excess water into the canals though it is not required. And then there is unequal distribution of water among the farmers. Some farmers complain that I'm not getting enough water, some are wasting water, and these kind of situations may be addressed if we understand and then quantify all these loss components, and then see which of them is a significant loss for us, how we can reduce these losses, how we can make water use much more efficient. Of course, there is a possibility that this crop water use also could be modified by suggesting farmers that please cultivate only less water intensive crops, water saving crops. But that is a possibility. But let us, for the time being, take that the farmers have been cultivating diverse crops and then they stick to their choices. But still, there are several other loss components that we can take into account and then try to reduce the water losses. One such thing is the evaporation, another is the seepage loss. And then there is an excess flow which can be addressed by proper scheduling of irrigation supplies, and then some fixing of leakages and pipes. See, in a typical lift irrigation scenarios, so you may experience that there is a lot of seepage losses. If the canal is passing through a very porous material, sandy soils, and then it is not lined properly, there is no cement lining or then stone lining given to these main canals or branch canals. So this, for example, comparatively, this could be around 20%. of the total loss, whereas the contribution of evaporation could be around 10%. And then if you find that okay, there is also some 10% of loss because of these excess outflows, and some 5% is the contribution of loss by the leakages, and then pipe joints and loose pipe joints and situations like that. So in such a situation, so we can prioritize which are these things that we can take up and address, instead of considering everything in a precise quantification and then addressing all those components. We may prioritize one or two. For example, the seepage losses. And these obvious loss, and we know that the soil absorbs a lot of water because it's sandy, and then the canal is unlined. So there is a possibility of converting existing canals into lined canals, or you may think of replacing some of the branch canals or some other field canals into pipelines, so that the using PVC or some other material, so that the transmission losses, the seepage losses, are reduced. So this is how we look at water auditing. So when we apply these principles of water optimum utilization of water in an agricultural scenario. So primarily, what we have done is that we have noticed and then identified different components of water application, water use, and water losses, and then try to quantify them. Out of them, we try to find the low-hanging fruit, which can easily be addressed, and then try to make intervention. So what follows from water auditing is obviously you plan some interventions so that the efficiency improves. Sorry. So this is how we apply these principles. And then now I will take you to a different setting. So here let us take a case of an urban water supply to a residential colony. See, this is the case of a colony in Hyderabad which is receiving bulk water supply from the Hyderabad Metro Water Supply Board. The Hyderabad Metro Water Supply and Sewage Board is an institution set up only for taking care of water supplies, and then also the sewage generated their collection and then treatment and all those processes. Normally in urban areas, cities and towns, there are municipalities or corporations handling water supply as well as sewage management. But here in Hyderabad, we have a separate institution. That's why so this water board, in short, it is called. It supplies water to many areas, residential areas, the industrial areas, as well as commercial establishments. And there is also a practice for several years that they give bulk water meter connections. They are metered bulk supply connection. So these connections, one of such colony is this one. This is in fact a real case where this is located in Kukatpalli area. The colony name is called Jalavayu Vihar, and in this case, the water supply, this board gives a bulk supply, and it is metered here. There is a meter placed here, and then this water supply goes into this underground sump. This is within the colony premises. The colony area could be around approximately 15 to 20 square kilometers. And then whatever water that is released by this board comes, and then it is stored here in this sump, and then further it is lifted up into the overhead reservoir, and from the overhead reservoir water is distributed to all the residents. There are about 85 residents, and then the Residential Welfare Association, in short, it is also called RWA. RWAs operate, and then they operate and maintain the water distribution system. So the responsibility of water board is to give bulk supply, and the responsibility of RWA is to store it and then distribute to the residents. Also, they issue every household some bill, and then they collect the water charges. Of course, in the not metered, but in a flat tariff is collected. Say, for example, every month 400 rupees is collected from all the households, and that money is used for maintaining, cleaning, operation, and maintenance of this water distribution system. But then The water board charges the WRWA as per the kiloliter basis. 1 kiloliter is 1,000 liters, and that is equal to 1 meter cube. So they will give every the commitment between this water board and the RWA is that every day approximately they will supply 90 kiloliters to this residential association as a part of their agreement. But in reality, the water board is not able to supply exactly 90, but it may supply sometimes because of some shortages in their supplies. It is 70 kiloliters. Sometimes they may increase it to 120, 115 kiloliters. So the supplies also are fluctuating. Then, apart from this water supply scheme, the RWA also has some bore wells located within this area, which are in the common lands, and so these are assets of RWA, and these are mostly pumped out and used for uh, gardening purpose. And then residents also have some bore wells in their premises. They are private bore wells. They also use to supplement the supply received from these river waters. So there is also groundwater usage supplementing the use of this water supply given by the Hyderabad Water Board. And then coming to the issues and problems identified, there is one is that this, as I said, irregular supply of from the water board, and then there are a lot of unaccounted for water, which means there is some water is supplied to the residents, but some water is missing because there are no meters installed at each and every houses. So there is no account for how much is supplied, how much is lost, how much is billed, and such kind of problems. Also, at the same time, the tail end issues are there. Some people complain that I don't receive sufficient water, and some people complain that see that person is having 4 cars and they always wash all the cars with this water, and so they are wasting water. So there is some elements of leakages from these network and then piping systems. So somewhere shortage, somewhere there is a surplus, and then so wastage. See, all these kind of issues are there. So when you write these things in the form of an equation and try to see where we can make intervention and improve the things. So on the left hand side there is a bulk supply. I am only writing this equation for the supply from the water board. So the bulk supply quantity of total water supplied, for example, say per month, is on the left hand side, and that is equal to there is some consumption by the residents. There are some leakages from this sum. Yeah, the sump is also much older one, and so there is a suspicion that whatever water that is filled into it is losing some of it because of leakages, and then finally it is getting into as a recharge to the groundwater. In terms of water budgeting, we have discussed it as a positive element that it is a recharge, adding to the groundwater reserves. But here it is a loss. Here, whatever the fresh water treated and supplied by the water board is now lost to the groundwater because of leakages from the sump. So, if that is really true, then we need to look at that. What kind of, how much of leakage is taking place? Whether is it possible to plug that leakage? So there is also leakage from the pipe joints because in the network there are several pipes and joints. There are walls, and then this infrastructure has to be maintained. There is also wastage by the residents, and these are all the components added up together is equal to the bulk water supply. This is how we balance various water components in a supply system. And then if you look at say the major components that are causing the losses to us, there is one is the leakages from the sump, which is a very obvious one, which can also be measured, easily detected. And then if it is rectified, then there is a possibility of saving a lot of supplied water from the uh, leaking to the groundwater. Another area is the leakages from the pipe joints, and then we can also educate residents about the current situation, the fluctuation of water supply, irregular supplies, insufficient supplies from the board. So we have to be more judicious in using the water, and such kind of education campaign also can go on. And also RWA can think of installing meters at every household so that how much water is consumed by each household may be measured more precisely, and then so you can quantify that how much is the actual consumption. Otherwise, in the current situation, we don't know exactly how much is consumed by the residents. So this particular component is not clearly quantified, but this should, by metering, this also can be done, and then maybe plugging the leakages from the sump will help us to save some water. And this is how you look at water auditing uh, from the in the perspective in a particular case of urban colony. Of course, we discussed in case of a very small colony, the same principles apply to much larger areas. A zone in Hyderabad or entire city of Hyderabad also may be taken into as one unit and see what are all the sources of water coming into Hyderabad from Krishna River, from Godavari River, from so and so tank, from so and so dam, and then what are all the demand side utilizations that are taking place. One is water used for the residential purposes. Another is it is supplied to the industries. Another is that it is supplied to the various utilities or these are commercial entities. And some part of the water is also supplied to the slum areas as in the form of tankers. So bring all those various elements into consideration and then make a assessment of each component and see where we can improve the efficiency and reduce the wastage of water. This discussion goes well for the urban areas, and then now let us the final one discuss about the water auditing principles applied to an industrial scenario. The industries, uh, many industries like steel industry, or textile industry, or automobile industries. Each industry in itself is quite different in the way the kind of activity takes place there, the processes, the different kinds of manufacturing takes place, and then the amount of water used, the water requirement, all that is different for each industry to industry. If at all we have to do an industry water audit, then fundamentally we need to understand some basics about that industry. What is that industry is all about? What happens in that industry? What kind of processes are there? How they use, where they use, in what form they use this water? This understanding is required. So here in this case, I am actually presenting a case of a steel plant which is located in Anantapuram district of Andhra Pradesh. This is nearby a town called Tadipatri. This is a very huge steel plant producing steel steel blocks, something like this that you see in the picture. So they take the raw material, iron ore, they clean it, and then through the process of smeltering, it is called smeltering. And through smeltering, they clean it, separate it, they melt it, and then so iron is separated, and then in the furnaces, once it is in the liquid form, they cast it into the kind of shapes that are required, and then chromium probably is added to make it as a steel, and then rust proofing and additives are added, and so finally this comes out. So this the product is again taken by some other industries and used this material is used to make their own finished products. For example, in a car industry, if they need some steel, and then they collect this material from there, from here, and then take it and then bend it required to the shape it, and then uh, give it a final finishing, and then all that is done. So this industry, uh, in this process of from the raw material iron ore and then making steel, see, they use a lot of water. See, for example, the, there are several processes where the water is required. Primarily, water is used in two kinds of processes. One is the consumptive purposes, another one is a non-consumptive purposes. See, consumptive means the water is lost, water is consumed in the process of manufacture. whereas in non-consumptive purposes, water is not consumed, but it is only the food. It is used in, and then it is again after the process is over, it is still available. For example, if you boil the water, the steam is generated. Steam is used to run a turbine, and then after turbine is runs, then the steam loses its energy. But as steam, it is available to us. We can cool it, and then again that water is that is cooled down can be again used for other purposes. This is called the non-consumptive purpose. So let us see here. This particular industry, this particular industry has a source of water from a nearby river called Penna River, and from the bed of that river, there are a number of wells dug. Some of the owned by these companies, some are owned by the private individuals, farmers, and then the company hired them these wells from them. And so several multiple wells are used to pump the water, and all that water is brought into pooled and brought into a storage tank, something like this you see here. This one is the kind of storage tank, a very large area. So obviously, once it is stored for several days, there will be losses due to seepage and then evaporation. That is quite possible. And then the water that is stored here will be taken into different supplied to different units of the company, like a smeltering unit or a boiler unit or some other process unit, and then that indent is given from these units to a department called utility department, and this utility department will see, okay, this much is required for this particular unit, and so they allocate and then ensure that it is that much water is available to that unit. Otherwise the process of industrial, that manufacturing process, gets suffers. Here, in some of these water uses, for example, uh, water used for cooling. After the iron is melted and then it is uh, heated up, then there is a somewhere it is required to cool it after shaping it properly. So for the cooling, water is used, and once that it water absorbs the heat and then cools down these iron members. So that water again it can be recycled for other purposes. And then, such as this, the water from the cooling towers may be reused for washing the floors or for sanitation purposes, or for again going back and then feeding the boilers. Boilers need continuous supply of water because the water is converted as vapor, so it has to be made up again. So boiler makeup also is required. So such kind of internal circulation and reuse also are happening already in this industry. And at the same time, there is also one thing that, for example, in the case of a boiler, when you are supplying water to a boiler, it has to be at a very low TDS standards by water quality. The ideally the TDS level should be between 0 to 10. Then only it is suitable for boiler application, because if water is heated up and then the salts like calcium and magnesium carbonates and bicarbonates, they precipitate and then form something called white colored scales within the boiler, and over a period of time the boiler's life is affected, its function completely goes defunct. So in order to avoid such situations and then extend the life of boilers and also its efficiency, it is always low TDS water is supplied it. So the water that is taken from the wells is taken into a clarifier, and then it is treated for turbidity, and then later it is taken to an RO plant where it is the TDS levels are reduced to the desired levels, and then only water is supplied. At the same time, from the RO plant, if there is anything called a reject waste RO reject, which will have very high TDS values, that water also can be further treated and used for some purpose like toilet flushing or any sanitary applications. This is a overall picture of the steel plant, and then we made a study of this steel plant and its water uses, and then here are the major findings. See, we find that in typically in any steel plant and also here, only about 10 to 15% of the total water is actually used, and for the consumptive purpose. That means which cannot be revived, which cannot be taken back. But then 80% is recoverable. The rest, lot of water can be from these the cooling towers or from the boilers and the vapor water that is used for running the various machines and turbines. And all that water is possible to recover and then again use that for various purposes. So here are the four major water uses. One is the cooling applications, which can easily be recovered. There is a process water, so you like wash the iron ore, and then after that there is some liquid waste is generated that can be treated and used again. And then there's a boiler feed water, so you feed it into boiler and then water vapor comes and the vapor is cooled down again, it can be used. And then the residential and sanitation etc applications where there is a lot of water is also required, because in the this particular industry there are about 5 to 6,000 people employees working at any point of time on a 24 hours basis. So there is a lot of residential facilities have created. There are food facilities and there is sanitation is required. Uh, so this is also one of the major uses. But then we mapped out all these into this kind of a small uh, schematic diagram. See, for example, if you see here, water is flowing in the Penna River in this direction, and then there is an expected that there is a dam will come up, and then some water will come. But currently, it is not happening. But most of the water supplies are from these wells on the bed of the river, and then this water is pulled into this particular storage pond, and there is uh, by the very nature there is a lot of evaporation loss happening because of the water storage. And the climate also is very harsh climate conditions in Anantapuram. The summer temperatures also go up to 46 degrees, 47 degrees. So there is also some amount of seepage and losses happening from the bed of this storage tank. And then after this water is taken into the clarifier where it is treated for removing the silt and then the solid particles, if there any dust particles are there. And after that it is pump house, and pump house handles water and supplies to different utilities, different units. So as part of it, water goes to the RO unit, where RO processes will reduce the TDS and supply the water to the boilers. Boilers they supply the vapor to the process units, and then after cooling that water vapors, the water is available for recycling and use. And so maybe partly that water is used to in smeltering process. And then anything that is wastewater emerging is recycling plant is there, the treatment plant, and it is once again used for cooling purposes. And this is how the plant operates. And then we found that major part of these losses, water losses and water inefficiencies, are found in the storage and then refining and handling of water. That means this is the area where we can do a bit interventions and more analysis, deeper analysis to see how how much of water is brought in, how much from the wells, how much is in fact used in the manufacturing processes, and what are the losses like evaporation, seepage losses, or any other leakages. So this is the picture taken from the Google Earth, and then this is the establishment whole steel plant location. Shows it's all the premises at one place, and you can see here the water storage pond or a tank where they bring in all the water from the bore wells here. This is the riverbed, and see that there is no flow of water. It is most of the time in a year. It is a dry riverbed, and then but there is water in the sand that is available for pumping. And the neighboring farmers also do agriculture using pumping that groundwater. There are few wells here, and the side of it, they just next to the river, and this water is pumped and to these storage tanks. This is how it's about 10 to 15 kilometers distance between these two locations, the river point pumping points and the pond locations. Yeah, let us now look at in more detail what, based on these kind of understanding, after looking at different processes that are taking place in the a steel plant, we have taken a 1 month record of the intake that is coming into this tank, the water storage tanks, and then the consumption, that means the outflow, how much water is drawn from this for various kinds of manufacturing processes. And so what is the net water that is added or removed from the pond storage. And against that we also taken measurements of actual increase or decrease in the storage, because there are scales installed in these ponds, vertical scales. There are simple scales which are demarcated in terms of centimeters and meters. Using that, we can actually measure what is the change in the storage. So, using these statistics, so we try to analyze what is happening in a month time and then see where are the problems. See, for example, in a given month, see the daily inflow outflow water budgeting is done. So for the storage tanks, so here we have done the water in a sense water budgeting for the storage tank as a central uh, the reservoir for us. Like earlier we did groundwater budgeting, taking aquifer as our storage medium. Here we have done budgeting, taking our storage tank as the storage medium. So that is how you can see draw some parallel between these two. And then the attempt is that, okay, then where is the unaccounted for water, and then whether there are there any losses. So the intake varies with water availability in the well, at least in the summer months. See, the intake depends on how much water is available in the wells, and sometimes this is varies. This was is very high, and there is generally around 6,000 cubic meters, but sometimes the availability goes down because of there is many electricity hours. The electricity is not available, or water wells are they have dried up, various other constraints. And so the supplies intake varies with season, also daily on a daily basis. And then on the other side, you see the consumption pattern. Consumption is also a variable. It is varying from, this is 3084,000 cubic meter to, there is also a 2010. That means somewhere between 2000 to 3000 cubic meters, 2000 to 3000 cubic meters. These figures are in terms of 1000 cubic meters. That much of consumption patterns are varying. It primarily depends on production targets. On any given day, the requirement depends on how much of final end products are manufactured, and then what is the targets. So both intake and consumption vary, but there are two other components, which are, one is the evaporation loss, another one is the seepage loss. See, this evaporation loss is on a continuous basis. See, whenever there is a sunlight and then heat, of course, there is also a need for wind speed. Wind also is required for evaporation to take place. So this is a continuous process happening. At the same time, there is also seepage loss happening from the bed of these irrigation tanks. Sorry, the industrial storage tank. So the seepage loss, it is because water is already stored in these tanks, and these tanks were constructed some time ago. We do not know exactly what is the bed is made of, and then what kind, how much is this seepage loss. There is a difficulty of quantifying and separating it, and there is, but of course there are empirically that can be quantified using some formulas. Whereas when it comes to evaporation loss, there is a bit of clarity in this. See, it is, though it changes from in the season to season depending on the daily sunshine hours, and then with seasons. But here, on for a monthly basis, when we take on a daily inflow and outflow, and then we compare it with the what is the actual change in the storage. So here it is the intake plus intake minus consumption, and is about this much on the first day. On the second day it is 29.4, but in fact this should be this much uh, is the amount of addition done. That means there is an addition of this much, but the storage has only what is added is only 29. That means a lot of water is lost either for evaporation or the seepage. And take for example, there is the pumping intake of 6050,000 cubic meters, and there is an outflow of 2,616,000 cubic meters. That means this much of water is brought in and added, but then you found that finally there is a change in the storage is only 3091 when you measure using a scale installed in these water tanks. So that means approximately 343.3 cubic meters was lost on that particular day, which is approximately say 343 cubic meters means 3 lakh 43,000 cubic meters. And but we still do not know whether this loss is predominantly because of the evaporation or predominantly because of the seepage losses. If we could separate these two, and if we find that okay, the evaporation is a serious problem, and it is the 70% of the loss is because of evaporation and only seepage is 30%, then we could as well focus on this first and then see how we can reduce the evaporation from the surfaces. See, as I said already, see the evaporation a lot depends on the wind speed also. So I will explain you how it happens. The evaporation process. See, for example, let us take this is the tank, and then there is some amount of water is there stored in this, and then because of the sun's heat and then sunlight, if water becomes water vapor and it goes up, and then it requires some amount of wind velocity flowing across on the surface so that it carries this water vapor along with this and then removes it away. Unless this water vapor is carried away by the wind, new water vapor will not emerge from the surface. So this is how the evaporation process is accelerated. So in case this wind velocity is very low, even though the temperature is very high, the evaporation losses will not be very high. So banking on this kind of this the basic physics, then we in fact suggested them that you can go for some wind breakers, so all around these tanks, so that you plant some trees which will grow very fast and then tall, and then work as a breakers, wind breakers, and so that the wind speeds will come down and the evaporations also will come down. At the same time, you will be making your campus, the industrial premises green. There will be clean the carbon dioxide. These plantations will work as the sinks of carbon dioxide. They produce more oxygen. The environment becomes better, and so you have much more multi benefits from this kind of intervention. And then of course any other kind of measures like to arrest the seepage losses, that is also good. So in fact apart from these windbreaker suggestion, we also suggested this plant, so that because Tadipatri town is very close by and there is a lot of sewage generated, and then all that sewage goes into a treatment plant. Currently it is the primary treatment is done, and then some partly treated water is coming out and being disposed. So why not the Arja steel plant install further treatment facilities there in the same premises, and then make it say tertiary treatments, and then make the quality water quality suitable for their use, and bring that water and then use it for various purposes, so that the dependence on the groundwater will come down for them for a period of time. So that is how the water audit was conducted in this industrial scenario. Hope now you understood how water audit can become uh, much more larger and then a complex, time consuming exercise. Because in most of the cases, you don't know exactly the various quantities of losses that are taking place. It has to be prioritized, some of them based on past experience or visual observations, or based on available information, and then focus on them, try to quantify and then address that. And then once it is there is some saving in water, you may go for the next one, and then uh, overall addressing the reducing the water footprints of that industry. So we now end these discussions of case studies. We have now first discussed about a simpler agriculture case study. There is a bit complex lift irrigation case study, and then we also discussed about urban water consumption, urban water scenario. Then we discussed just now about a steel plant and industrial scenario, and then how to conduct water audits. And now I come to here. This is, I think, last slide. So the standards for water auditing. So though there are there is knowledge about water auditing, there is some practice, there are research papers available, some case studies are available, but then there are no standards available for water auditing so far. There is no a standard uniform guidelines given for this is how it has to be done. So it is unlike GEC recommending a standard methodology for groundwater budgeting. Here it is a collection of various approaches and concepts, and you apply them, the combination of them depending on the situation. You make them tailor made for the problem on hand. So, but in recent development is that the ISO, which is the International Standards Organization, has come out with a new standard which is called 14046 in 2014, which defines how to assess and then how to report water footprints in mostly in industrial context. But these principles are very much useful even in the other context also. So it applies to various products like a car or some kind of processes or say agriculture where you irrigate crops and then or such kind of processes. Institutions, see institution as a whole, how much water is being used by it, and so they suggest that a life cycle approach has to be taken, starting from the beginning to the end of that life cycle of that product or process. The- that is the recommendation. And then ultimately, the goal of this water footprints analysis is that reducing negative environmental impacts due to water use. Ultimately, it gives us more insights into how water is being used and where there is a possibility of reducing, improving efficiency. And finally, it is just a framework for voluntary action. In fact, it is not binding, it is not legal, not legally adopted. And so it is a collection of good practices, methodologies, so that you voluntarily adopt them, reduce your water footprints, and then set an example for others to follow. Here, according to this standard, this 14046, there are three water footprints that they have classified. One is the blue water footprint, which is about surface water and then groundwater. So it is the surface water and groundwater when it is used to produce goods and services. It is called blue water footprint. So if you reduce your surface water use, groundwater use, then you are reducing your blue water footprints. When it is called green water footprints, see that means the soil moisture, the available when it is used for producing goods or services, then it is called green water footprint. Similarly, when some pollutants are emerging from the industry, and that is some water, fresh water is used to assimilate and then treat that pollutant, recycle it, then that kind of water footprint is gray water footprint. This is how basically the standard defines. And coming to the Indian industrial situation, there is, in fact, in recent years, a lot of change in the mindset coming. They are adopting recycling, reuse, and optimization methods in many industries, and then even in urban processes, but mostly because of economic compulsions than any statutory regulations. So let me explain you that as water becomes scarce, and then you have to bring water from very long distances and then buy water a very high cost, then industry and then the institutions are becoming more conscious of, okay, I can reduce the cost of buying water, and then by adopting these recycling, reuse, and approaches, optimization approaches. That is how the industry began adopting these practices. Uh, but in fact, there are certain local regulations that are in place. For example, in this steel industry case, say they draw a lot of water every day. And so the groundwater department has regulated that, okay, you should recharge double the amount of rainwater by doing rainwater harvesting and conservation works. Mm, That is that's how they got the permission to exploit groundwater. And so there's the local regulatory restrictions are also some sorry sometimes the local regulatory guidelines and restrictions are also helping to prompt these industries to go for more and more taking steps towards groundwater recharge or water conservation, or reducing their wastage. Even in some cases, the sewage that is coming out, the effluent water, that is wastewater coming out from the industries, there are certain regulations. So to comply with those regulations, these effluent is taken to a treatment plant, and as much as possible it is treated, and water is reusable water is extracted from it. So this is the general scenario related to water auditing, and but definitely in coming future, as more awareness is going to come, more restrictions, regulations are going to come, and then water auditing is going to be the a mantra for all the industrial, especially industrial processes. Even in the urban context, many cities are now operating at 30% losses, 40% of losses, 50% losses, and then as the water shortages become more and more intense, so we are going to have all these water auditing mechanisms in place more in urban water supplies also. So this I think this is the end. With this, I will stop my discussion